Boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to The Naked Scientists with me, Chris Smith, and also with Helen Scales. Hi, Helen.
Hello.
Now, coming up this week, our scientists have found a way to bypass a severed spinal cord and relay brain signals straight to muscles, and that might hold the key to getting paralysed people moving again. Also, how the colour of the picture on your television could affect your dreams, more on that in a second, and how the remains of a chemistry experiment that was carried out over 50 years ago has actually helped to reveal a lot more than we first thought about the origins of the building blocks of life here on Earth. That's all on the way. Helen.
Thanks, Chris. Also this week, we're taking a look at the science of nuclear fusion to find out how researchers are trying to recreate the process that powers the sun down here on Earth. The promise, of course, is bounteous supplies of cheap, clean energy. But how close are we, and is it even possible? We'll be talking to fusion scientists Steve Cowley and Kate Lancaster to find out.
Thank you very much, Helen. And when it comes to creating nuclear fusion, of course, size does appear to be very important.
It has to be a certain size to produce a certain amount of energy. That is what physics teaches us. Small machines can only do a little bit. Larger machines can do much better. And then a reactor will even be larger than JET.
Mira's been down to JET, that's the Joint European Torus, the first machine to harness the power of fusion, and we'll be hearing how she got on later in the programme. So if you've got a question for us about the science of the sun and nuclear fusion, then do get in touch. The email address is chris@thenakedscientist.com.
The Naked Scientists Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
This week, scientists have made a giant step forward, really, in a bit of work which might help people who are paralysed because they've had a spinal cord injury to get moving again. They've shown this just using monkeys to start with, but monkeys are a very good model for how humans work, so we think the same technique should work in people. This is Chet Moritz and his colleagues. They're based at Washington University in Seattle, and they've got a paper describing what they've done in this week's edition of the journal Science. Now, their approach has been to put an electrode into the brain, and specifically the motor area of the brain, where the brain encodes signals about what it's planning to do in terms of making movements. Now, in people who injure their spinal cord, the major problem is that those planned motor movements can't get from the brain down to the connections to the muscle so the person can move. And the brain and spinal cord, when you injure them, do not regenerate or repair themselves very well, if at all. So we need to find a way to bypass that break. What these guys have done is by recording that neurological chit-chat from the motor area in the brain and using a computer to decode it, and then turning the computer signals back into a stimulatory signal that's fed into the muscles of the monkey's arm, they're able to get a monkey with a paralysed arm, just temporarily paralysed with some anaesthetic, to learn to play a computer game just by the power of thought. And they've shown that just by recording from a couple of nerve signals, the brain of the monkey can very quickly learn to adapt how it responds to the screen where the monkey's playing a video game so that the monkey can move its paralysed limb. Early days yet, but very exciting, because what this reveals is that we should be able to do the same thing in humans and therefore help people who have these kinds of injuries to get mobile.
Sounds fantastic. Well, from things going on in the brain to something else that happens in the brain. Chris, do you dream, when you dream at night, do you dream in black and white or in glorious technicolor?
I definitely have colour dreams.
You dream in colour. Well, whatever your answer might be, it could well depend on what sort of TV you watched as a child, because a new study has provided more support for a theory that's been around for quite a while, that people who only watched black and white television and movies as children also dream in black and white instead of colour. Now, this study comes from Eva Mersin from the University of Dundee here in the UK, and she basically tried to address the age-old problem, one of the problems with dream studies, which is how to accurately get people to report what happens in their dreams. Because as you all know, I'm sure, you very, very quickly forget what happens in your dreams. And it's easy to kind of mould that idea a bit later on in the day, even, half an hour after you've woken up. And what she did was she recruited 60 people to her study. Half of them were under 25, half of them were over 55. And she gave them a questionnaire to find out what sort of TV they watched as a child and what dreams they were having. And these are the sorts of methods that were used a while ago, back in the 50s, when people still reported that they were dreaming in black and white. She also also did something where she asked her subjects to complete a dream diary as soon as they woke up, which is the sort of technique that was introduced a bit later on when people started suddenly saying that they were dreaming in colour, which does seem to be what happened, that there was this very quick change through time in the 20th century to colour dreaming. Now, she found that exposure to black and white TV as a child could still really quite strongly influence the dreams you have 40 years later. In the younger age group, she found that only less than 5% actually of people dreamed in black and white, and of the older folk who did have access to colour TV, around 7% of them still dream in black and white, whereas 25%, quite a lot higher, of the older age group who only had black and white TV as young people still dream in black and white.
One wonders what extent recall bias plays a role here, though, and whether you could actually do a study where you took those people who say that and then expose them to a lot of colour TV and see if it does distort their dreams, or perhaps they just really like plugging into really rubbishy old movies.
Well, it's all quite mysterious still, I have to say. One of the theories about what determines our dreams in a kind of long-term sense is that perhaps they're quite plastic up to the age of around 12. So you'd have to do this with young kids, and then they'd be dreaming black and white for the rest of their lives. I don't know.
It depends if it's ethical to expose them to some of the rubbish that was on television in black and white.
Absolutely, I don't know, but it's all about the emotions of movies, and that could well be in television. We get so wrapped up in it, and that could be why we dream in those colours. I mean, perhaps the only way of finding out for sure what people are dreaming, what colour they're dreaming is to take the people who can lucidly dream and control their dreams and somehow come up with a signal while they're actually dreaming for them to say, yes, black and white or colour, and while they're actually in their sleep. But that's also difficult because you may be influencing the way they control their dreams. But I also want to know, what about the people who watch no TV at all?
Quite. And one other thing is that I had a friend who was blind who said to me that some of his friends who went blind later in life loved going to sleep because it meant that they could see again, and also they could recognise or remind themselves what colours look like. So those people definitely dreamed in colour. Those people were older, because this friend of mine was in his 70s when he died, and he had friends of a similar age, and so his friends were saying that they'd gone blind in later years and they dreamed in colour. So I'm not entirely sure that television is that much of an influence, but I buy the fact that you're saying that it might kind of tip the balance a bit.
It could be interesting, and it's all maybe about partly what we think we should be dreaming, and if everyone says they're dreaming in colour, then you might well just convince yourself that you are. Don't know. Very mysterious, but rather wonderful as well.
Let's wind the clock back about 4 billion years or so to the origins of life on Earth. There's been a controversy raging for many years about where the building blocks of life, in other words, the complex molecules that our cells use to assemble all of the things such as the enzymes and other machines in the cell that make cells viable, where those chemicals come from. And about 50 years ago, a scientist who was very interested in this was Stanley Miller. He was working at the University of California at San Diego, and he had got into the idea that perhaps the conditions on early Earth were sufficient to spawn the chemistry that produced all these building blocks. And so he decided to recreate a sort of mock-up early Earth in his laboratory. And the way he did that was by having a flask in which he put some water, which he could boil. And out of the top of this little round flask, he had a spout that the steam could come out, and it would go into a very big round flask, like a spherical flask. And in there he had 2 big tungsten electrodes, and he could detonate lightning to go between them. And so he added to this apparatus some water, some ammonia, some hydrogen, and also some methane, which were gases we know were in abundance on the early Earth. And he set this thing discharging and running for a while, and then he analysed the deposits that built up inside, and he was able to show in 1953, published a paper in Science, he had found at least 5 amino acids, which are the building blocks of proteins that we think are essential for our cells to be able to work. So this kind of suggested that the Earth was a very good melting pot in its early years. It could make the complex chemicals we need for life. Thing is, lots of people said, well, this is a bit artificial, and 5 chemicals doesn't make a viable organism, does it? And this kind of got consigned, quite literally, to the shelf, because Stanley Miller died last year, but Jeffrey Bader, who still works at University of California at San Diego, was his PhD student. And when Stanley Miller died, he gave all the things in his lab to Jeff Bader, who found out from someone else about the existence of this cardboard box on a shelf in his lab. And so he went to this shelf, and there was this cardboard box with all of Stanley Miller's apparatus in it, including hundreds of little flasks, which were the original flasks that contained the products of all of these reactions he'd done. And so he thought, what would happen if we subject these to modern-day chemical analysis using modern techniques? So they took some of the flasks, and they've got a paper in this week's Science where they show feeding these deposits back into complex machines that will analyse them carefully today, and they've not found 5 amino acids. They actually stopped analysing when they got to nearly 30 chemicals of complex molecules that had been made in this apparatus. And his argument is, well, this adds a lot of credence to the idea that the Earth was a very prolific spawner of these kind of molecules. There could have been volcanoes that would have splurged up water and lots of these gases. There would have been lightning storms, and so the conditions that Stanley Miller envisaged 50 years ago or more could well have existed and probably did produce the complex chemistry that we depend on ultimately today.
It's quite astonishing that something sitting on a dusty old shelf could really have been overlooked all that time and then suddenly brought back to life with the modern wonders of the scientific advances. But I'm going to wind the clock back forwards again, staying in the natural world, and to coral reefs, one of my favourite places, and the fish that spend their lives picking clean other bigger fish. And if they work in pairs, it seems, they actually will provide a more honest valet service than when they work on their own, showing that it probably pays to cooperate and behave. Now, this is according to a study in the journal Science this week from a team led by Redwan Bashari from the University of Neuchâtel in Switzerland. Now, if you've ever been diving on a coral reef, if you've been lucky enough to do that, or if you've watched a TV documentary, you might have seen something called a cleaning station, which is where small cigar-shaped fish called wrasse and also some types of prawn congregate and actually dance around and advertise their services for hire as cleaners, and they pick off bits of muck and dead scales and parasites from other fish. Now, when cleaner fish work in pairs, they're posed with a prisoner's dilemma. Should they cheat on their client fish and on their partners by taking a mouthful of nutritious mucus instead of plucking off a parasite? Because it turns out that cleaner fish actually much rather eat mucus than do their proper job of cleaning. But when they do, it's usually their last mouthful because it gives their clients a nasty nip and sends them swimming off in a huff. So honest members of a cleaning duo run the risk of actually losing out twice over, because if their cheating partner sends off the client when they themselves haven't actually had a morsel of mucus to enjoy. But this new study actually suggests that as long as the fish being cleaned decides when it's time to leave, the cleaner fish working in pairs are much less likely to cheat than when they work on their own.
And so the implication is that the model fits what we see?
Basically, yes. This was a model that was worked on a computer. They then went out and looked on coral reefs at what was going on and found that there was much more honesty, much less nipping. And actually, this is you can see the big fish kind of jolt, and that's because they were like, oh, ow. They haven't maybe actually got to the point of swimming off, but they've definitely been nipped. And that happens much less when they're working in partnership. So yes, it definitely pays off because obviously the pair of fish are getting more food, and the client fish is getting cleaner. So it works for everyone. And this could also apply to other things in the natural world that work in partnerships like that, like nitrogenous bacteria in roots. And there's a type of butterfly that allows ants to stay and defend it by giving them sugary secretions to feed them on. So there's all these partnerships, and they're very stable and work very well.
Thank you, Helen. You do a wonderful impression of a fish being nipped. Brilliant. Now, also in the news this week is a new way to fight back against an invasion of aliens. Now, we're not talking about little green men from space. We're actually talking about plants that have been moved from one country to another. And when they move to the new country, they become a highly invasive species. And one here in the UK, which came to us originally from Japan, was the Japanese knotweed, Fallopoeia japonica. Now, it's a very pretty plant, has nice white flowers, but once it gets into the wild, it goes absolutely mad, and it starts pushing out all of the native species. Scientists are suggesting that perhaps we should bring in another species to deal with this. Now, we've heard this story before in other countries, and it's turned out to be an absolute disaster. So we thought we'd go to someone who might know the answer as to whether this is a good idea or not, someone who's worked on knotweed for a very long time. That's John Bailey from the University of Leicester. Hello, John.
Good evening.
Welcome to The Naked Scientist. Just tell us a little bit, if you wouldn't mind, about knotweed. What is it?
Well, basically, it's in the Polygonum family, which we know mostly as docks and things like that. And it's part of a giant herb community. And it's actually herbaceous. Although it grows to sort of 2 or 3 meters a year, it dies down, and the resources are preserved in a woody rhizome.
So why is it such a pest?
Well, there's nothing magic about it. If you found a rosette that had just started to grow and weed killed it, it would kill it stone dead. The problem is that in established colonies, there are enormous amounts of biomass stored under the soil, going down some meters.
Meters underground? It's actually got rootstock from which it can regenerate a plant?
Technically, they're rhizomes, so they're woody stems, and I've got some pieces of wood from these things, and, it could do someone a nasty injury with them,
So they're pretty robust. What are the scientists suggesting this week that we do in order to weed out the problem?
Well, basically, one of the reasons it's so successful over here is that it's left all its predators behind. I mean, in Japan, you rarely see an undamaged plant. And the idea is that by sort of producing a sort of slightly more level playing field, you've tipped the advantage in favour of people who are actually trying to control the plant. What
pest are the scientists suggesting that we bring into the UK in order to get rid of this plant?
Actually, a little bug, a true bug, Athaleria itadori, and it's a sort of leaf sucker. And in laboratory tests, it's proved very encouraging.
How do you test out whether or not something's going to have knock-on effects? So it might just start tackling the knotweed, but then it might develop a taste for other native species, and as it's another invasive animal, it might then cause more of a problem.
Yeah, quite. Well, I mean, the testing is sort of comprehensive as possible. So first, it's what's called a centrifugal host testing. So first of all, you look at species related to the target plant, so particularly crop plants, so perhaps rhubarb, buckwheat, any endangered species. I think we have a species of dock shore dock that's endangered. Second, you look at host plants of species closely related to the candidate organism. Then unrelated plants with morphological or biological characters in common with target. Because although some insects are very good taxonomists, others will go for particular biochemical parts of the plant. And then finally a range of crop plants, particularly those that have never been exposed to the candidate agent before.
But there's not really any substitute for the real world, and then there's always the danger that you might have missed something, isn't there?
Oh, absolutely. I mean, you can't cover absolutely every eventuality. You can just sort of, within the sort of 99%, assurance.
And finally, John, do you think this will actually solve the problem?
Well, I tell you, it certainly won't be a magic bullet, and the people promoting it don't believe that either. I mean, you've still got to carry on educating people about not removing these plants, about not sort of spreading these plants, and you've also got to carry on with the conventional control measures.
And, of course, not introduce them in the first place. Thank you very much, Dr. John Bailey from the University of Leicester.
Distilling the best science. The Naked Scientists.
You are listening to The Naked Scientists with me, Chris Smith, and me, Helen Scales. I knew I'd get that wrong, sorry. Still to come, we're going to be going nuclear and finding out about the physics of fusion. But first, let's find out what Ben and Dave have been up to this week in this week's Kitchen Science.
For this week's Kitchen Science, Dave and I have brought a microwave into an electronics lab at Long Road Sixth Form College. And with me I have Michael and Andy. And what do you guys study here?
Physics, biology, electronics and computing.
And Michael?
Electronics, physics, maths and environmental studies.
So really us turning up in an electronics lab with a microwave seems about right for your sort of stuff?
Yeah, pretty much.
Dave, what are we doing today?
We're doing an experiment to see what happens if you put a grape in a microwave.
Won't we just get a hot grape?
We'll probably get a hot grape, yes, but with any luck we would get something else quite interesting.
OK, so people at home should just get a microwave, put a grape in it and turn it on? This really doesn't sound much of an experiment.
Slightly more subtlety to that, although not very much. What I want you to do, Andy, is take a grape and then cut it in half, but not quite all the way through. So there's just a little bit of skin holding the two halves together.
All right.
OK, then, so Dave's handily supplied a knife. Now, obviously, Dave bringing knives into schools. Good job there isn't a metal detector on the gate. So we need to carefully slice through the grape, leaving just a little bit of skin on the side. So we just sort of peel it open so that the grape is almost completely cut through, just a little bit of skin holding the two together.
And then it tends to work better if you can just dry the bit of the juice off at the joint. So just get your finger and wipe off the juice in the middle. Sorry, I'll get your fingers covered in grape juice.
Well, the best science experiments tend to be messy. OK, so we now have a grape. In fact, what we'll do is do a few grapes because it doesn't always seem to work. So if we put a few on the plate, then that should set us up for a proper experiment. What do we do next?
Put it in the middle of the plate. Put the plate in the middle of the microwave. And turn it on for 10 or 15 seconds and see what happens.
So, Michael, what do you think is going to happen?
I have no clue what might happen, actually.
Andy, any ideas?
Hot grape.
Hot grape. All right, then. So it looks like we might be making a hot grape. But if you want to have a go at home, just slice almost all the way through a grape, leaving just a little bit of grape skin connecting the two halves. Pop that in the middle of a microwave for 10 or 15 seconds and let us know what happens. So we'll be back later in the show.
Thanks, Ben. So we will join them later to see what they've done. But, of course, this couldn't be any easier. If you want to have a go right now at home, all you need to do is cut a grape nearly in half, leave a little thin bit of skin joining the two halves together, and put it in the microwave for a few seconds. If you've had a go and you want to let us know what happened, we'd love to know. The email address is chris@thenakedscientist.com.
We've had a couple of emails and things come in, Helen. Connor in Tillingham says, how do people who are blind from birth actually dream? The answer is, I know the answer to this because people have told me, because my friend who I mentioned earlier was blind from birth, and he tells me that his dreams were just mainly words and sounds. In other words, the kinds of things that you're exposed to that you have experience of experiencing, and so he would just experience those. Also got a question, a comment from Andrew Steer in Cambridge. He says, we had a black and white TV until I was 5 years old, but I definitely dreamed in colour when I was under 5 years old.
Yes, I think this study did definitely show that it was all, it was more that it tends to make people more likely to dream in black and white. It's not everyone, but that's very interesting that that's what you said. Thanks very much.
And we've got a question from Les in Over who says, if nuclear fusion's so clean, why is there so much radiation in space? Well, the answer is, of course, that in space there's nothing to stop the radiation, and so there's a sort of million-mile-an-hour maelstrom of cosmic radiation which is streaming off our own sun. And if we didn't have the magnetic field of the Earth to deflect it away, then it would be basting us in radiation. It would also be plucking away our water and our gases from our planet, and we would end up like Mars ultimately did. So it isn't a safe and nice hospitable place in space, but it's not just because of the use of fusion that it's not. This is The Naked Scientist with Chris and Helen. We're talking about the science of fusion, and if you'd like to join in, the email address is chris@thenakedscientist.com.
Laying the facts bare. I say. The Naked Scientists.
Now, fusion power is the thing that powers the sun, so we know it does actually work, but the big question is whether or not we can get it to work here on Earth, which is what we're going to be looking at this week. But first of all, to give us the basics of what nuclear fusion is and what it means, we have got with us Professor Steve Cowley. He's from the Culham Fusion Science Centre in Oxfordshire. Hello, Steve.
Hello.
Welcome to The Naked Scientist. So, fusion, how does it differ from fission, the thing that powers the nuclear power stations we have here in Britain?
Well, behind all these ways of making energy is the fact that the most stable nucleus of an atom happens to be iron, right in the middle of the periodic table. It's a medium-sized nucleus. And any way you can go towards it, you can gain energy. So fission is splitting very big atoms, nuclei of atoms, to go towards iron. And fusion is joining very small ones together to make bigger nuclei to get towards iron. But it turns out the easiest reactions to do with fusion are to join hydrogen together to make helium.
Is that why if you look at a star like our sun, as it ages, it builds up a core of iron because it's fused all of its products to make iron, and that's when it runs out of energy, so it blows up?
So stars start with hydrogen and a little bit of helium, and they join the hydrogens together to make helium, and then they join the heliums together and they make carbon and oxygen and all the things that life is made of, and gradually work their way towards iron. And when they burn out, some of them burn out before they get to iron, but the bigger ones go to iron, and that's how you get iron, that we have on Earth.
So let's look at the nuts and bolts of the fusion process then. So you have a star which it starts off as a big ball of gas which collapses in and gets warm as everything rubs together and gets compressed, and that's largely hydrogen. So how does it then start to join up and make these other things eventually to end up as iron?
So the problem with fusion is that in order to get them to stick together, you have to get them really, really close, because there's a force in the nucleus which is called the strong force, but it only acts over a very, very short distance. And there's another force, which is the electric force, which acts over a long distance. Now, when you've got two nuclei far apart, they repel each other because they're the same charge. Two nuclei are both positive charges, they repel. But when you get them really, really close together, they grab each other and stick. And to get them that close, you have to get over this repulsion all the way. So I always like to think it's a bit like having an enormous hill, but in the middle of the top of the hill, you've got an incredibly deep well. And what you've got to do is get your two hydrogens up to the top of the hill and to drop into the well at the top of the hill, and then you can release lots and lots of energy. So the problem is you've got to fire them together hard enough that they get over this repulsion. It's sort of like playing golf in some crazy golf course. You've got to fire the golf balls up the hill, let them drop into this well. So you've got to fire the hydrogen together really, really hard. Most of the time, they just bounce off each other, And then occasionally they get close enough together, they stick, they grab each other, they make helium, and, you get fusion from that. Now, it's a little more complicated than that, but the key fusion reaction that you want to do, the one that's the easiest to do, is between two isotopes of hydrogen, two kinds of hydrogen. One's called deuterium, the other's called tritium.
Why do you need those? Why not just standard belt and braces hydrogen?
Well, it's a complex process to take two hydrogen. Remember, helium is actually 4 particles in the nucleus, and ordinary hydrogen is just 1 proton. So when normally you fire hydrogen into hydrogen, right, you make a very, very slow reaction that really only goes on in the sun, right, to make an intermediate stage, which is deuterium. Now, deuterium is heavy hydrogen. It has 1 proton and 1 neutron. And in order to fuse those together to make helium, we do a reaction in our lab, which is the fusion of deuterium with another kind of hydrogen called tritium, which is 1 proton and 2 neutrons. You fire them together. For a moment, they all stick together, and then it disintegrates into helium and 1 neutron left over. And each time you do that, you release enormous quantities of energy.
And on the sun, what sorts of conditions are there presiding over this reaction in order to make it happen? In other words, what have we got to try and aim at here on Earth to get the same thing going here?
Well, on the sun, you've got 10, 15 million degree stuff there, which is called a plasma, which means that the nuclei are running around free. They're not in atoms anymore. They don't have electrons going around them. The electrons are running around free. The nuclei are running around free. And they're running around very, very fast. So they keep bumping into each other. And every now and again a fusion reaction happens. And the fusion reaction happens. It releases energy. It supplies energy to this very hot stuff in the middle of the sun. And more reactions happen. And gradually, over time, it releases that heat that works its way to the surface of the sun and comes out as light.
One thing that fusion has is a very clean image. It's viewed as a clean source of energy. The sun pumps out this cosmic wind, million-mile-an-hour maelstrom of charged particles, ions and radiation, which, if we get basted by it, is fatal. So why has fusion got this clean image, and why do we view it as the salubrious counterpart and a sort of reverse of fission?
So what you've got to do to make fusion happen is you've got to get something that hot. And in fact, in our experiments at Culham, we get things up to 100, 150 million degrees. Actually much hotter than the centre of the sun, sort of 10 times hotter. And at those temperatures, obviously you've got to keep it away from the walls, because if it touches the walls, it'll get cold. So we do that with magnetic fields. And when we do that, we confine this thing at 100 million degrees, this plasma at 100 million degrees. Particles are bouncing into each other all the time and making fusion happen inside there. But the radiation that comes off is confined both by the magnetic field and by the walls itself.
And that's why nothing can escape, we hope, in the long run. Nothing
can escape. So with fusion, we aim to produce a power that has no long-lived radioactive waste. Right? And the only problem with that is that you make a little bit of radioactivity in the walls. So you design the walls so that the radioactivity dies away very, very quickly.
Thanks, Steve. We'll be finding out a bit more from Steve in a second about how you actually do that, because he's going to stick with us and we're going to talk about the actual practicalities of making fusion happen. That's Professor Steve Cowley, who's the director of the Culham Fusion Science Centre in Oxfordshire. First of all, if you have any questions about the science of fusion, then do get in touch. Email us, chris@thenakedscientist.com.
Bringing the facts to bear. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and me, Helen Scales. We're talking this week about the physics of fusion. Later on, we'll be hearing from Kate Lancaster from the Rutherford Appleton Lab. But first, since we've had a little bit of an insight already from Steve into how fusion works and how it might provide us with huge amounts of relatively clean power, but what really is going on about whether or not we can make a mini sun in a lab? It's no mean feat, and how is it done? Well, we sent Mira Sinthalingham along to the Joint European Torus, which was the first machine to make a significant amount of fusion power. It was enough for 16,000 houses. She also asked some questions about the physics of fusion when she met up with Andrew Kirk and Jeff Ongenar to discuss the challenges involved in making fusion power a reality.
This week, I'm at the Culham Science Centre in Oxfordshire, which is home to the Joint European Torus Project, also known as JET, the world's largest nuclear fusion research facility. Nuclear fusion is the process that occurs in our sun to keep it burning, and if made possible on Earth, it could provide us with vast amounts of energy. Now, current work on fusion involves heating the hydrogen isotopes deuterium and tritium to high enough temperatures that they fuse together to form helium, releasing more energy as a result of this fusion. But it's proving to be a real challenge, because whilst there are techniques to heat and energise the atoms, such as using currents and beams of high-energy atoms, the real trick is to actually maintain these temperatures long enough for fusion to occur continuously. With me now is Andrew Kirk, a senior scientist here at the Culham Science Centre. So Andrew, fusion happens so naturally in our sun. Why is it so hard to recreate here on Earth?
OK, to make fusion happen, we have to get two atomic nuclei close enough together to make them fuse. That can only happen if the two nuclei collide at very high speeds, which means high temperatures, so tens to 100 million degrees centigrade. Once you've got particles at these temperatures, you've got to find a way of actually keeping them together and not making them melt any material surfaces. So what we do is we use magnetic fields to actually constrain the charged particles in the plasma and keep them away from these surfaces while we try to heat them up to these extreme temperatures.
And so how do you actually go about doing this and creating fusion?
Here we use a machine called a tokamak, which is a Russian acronym which basically means a magnetic bottle, which allows us to actually constrain charged particles.
And how does it go about doing that?
So a tokamak is a sealed vacuum vessel. The inside of a tokamak actually resembles a ring donut into which we inject a small amount of gas. Instead of using hydrogen, we use the heavier forms of hydrogen called deuterium tritium. We then take this gas and turn it into a plasma. A plasma is the fourth state of matter, so you know you've got solids, liquids, gases. But the next state is a plasma in which you've stripped the electrons off from the atoms. You've got the positively charged nuclei and the electrons together in effectively an electromagnetic gas.
And what happens once you've created this plasma then?
OK, what we then do is we use the magnetic field to shape the plasma and to keep it away from touching the sides of the vessel, and then we actually start to heat it.
Why do you need to keep it away from the sides of the vessel?
Because anywhere that this plasma comes into contact with the vessel, A, it would erode the material or damage the material of the vessel, but more importantly, it would actually cool down the plasma and it would stop the fusion happening, or you'd have to put in a lot more energy to actually keep the plasma hot.
But how does the tokamak actually do that?
We generate the magnetic fields in such a fashion that the charged particles, which follow magnetic fields, spiral around and around the tokamak in a shape that resembles that of a slinky spring. So they follow around in this helical pattern all the way around the tokamak. The slinky spring stops the charged particles escaping from the edge of the plasma and therefore keeps them away from the walls, and we put a gap of about 10 centimetres then between the edge of the plasma and the wall.
5, 4, 3, 2, 1, 0.
So I've now come to the control room of the JET project. Now the tokamak isn't actually very far, it's about 60 metres away from us. With me now is Jeff Ongenar, who's the task force leader here on the JET project. So Jeff, how big is the actual tokamak here? So we can only see a slight part of it, but how big is the overall thing?
The overall thing, including all the diagnostic and heating systems, is about 13 meters high and 30 meters in diameter. It has to be a certain size to produce a certain amount of energy. That is what physics teaches us. Small machines can only do a little bit. Large machines can do much better. And then a reactor will even be larger than JET.
So we're here now in the control room. What's monitored on the project from here?
The control room is in fact the place where we control and plan the experiments. So we set up all the physical parameters needed to run the machine for a particular experiment, to test out a particular idea. So every 20 minutes we can have a new experiment, and a new experiment means that we change another parameter, see what is the effect, and the final aim of all these experiments is to get to the best possible magnetic confining system. That means that we want to optimize the heat we need to get the reactions going. We want to optimize the time the heat stays in the machine, because that will then allow to run as efficiently as possible.
So we heard a few minutes ago that a pulse had just taken place, and we've got this screen here in front of us that has all the facts and the stats of previous pulses that have just happened in, say, the past couple of hours. It's all to optimise the confinement of the plasma to basically keep it at as high a temperature as possible. What has the energy output in relation to input been so far with the project?
JET was designed to show that fusion is scientifically possible. When JET was planned, we had only small machines, which fit more or less on a table, and Europe decided to take a bold step and to build a much larger machine to show that the amount of heat produced by fusion reactions could be equal to the amount of heat you need to get the reactions going. And we have proven that we get to about 70% of the heat back compared to the heat we put in. And I think with the current developments of the last years, if we try again, we will get much closer to 1 now, so that in fact the scientific possibility of fusion essentially is shown.
Are you now then hoping to create more output, i.e. create more energy than you are putting in, and therefore obviously having an energy source?
Yes. So in JET that will not be possible, because JET is not built like this. To get much more heat out, you need a larger machine. And this larger machine is designed and is now starting to be constructed in Cadarache in France, and this machine is called ITER, which stands for the International Thermonuclear Experimental Reactor. ITER is there to show that science and technology now go together and can be used to realize a fusion power reactor later.
Jeff Ongenaar, and before that Andrew Kirk, talking to Mira Senthilingam about the challenges that they face in making nuclear fusion a viable power source and the next steps towards developing a working power station.
You're listening to The Naked Scientist with Chris Smith and me, Helen Scales. And coming up later, we'll be finding out what happened in kitchen science this week. And you should be having a go at home if all you need is a grape. Cut it in half nearly with a little bit of skin left over to join the two halves. Pop it in the microwave for a couple of seconds and let us know what you found. But we will also be talking to Kate Lancaster in a minute about how fusion might be triggered using lasers.
But before that, thank you, Helen, let's go back to Steve Cowley, who is from the Culham Fusion Science Centre in Oxfordshire, and he's also the person who's one of the driving forces now behind ITER, which is the International Thermonuclear Experimental Reactor, which the guys talking to Mira were mentioning. They said size is important, Steve, and this certainly is certainly big budget. This is our best bet yet of trying to make fusion a reality, isn't it?
Well, it's going to be a fabulous experiment to be involved in, because it's going to produce 500 megawatts of fusion power. That's when you think that a typical power station is about 1 gigawatt, so about twice that. This is incredible. This is getting to industrial scale of fusion power. It's really showing that we can do it and that we're getting there. It won't actually produce any electricity, but it'll get us right to the very edge of being able to produce electricity with fusion.
So could you just paint us a picture of what actually is ITER, how will it work, and how will you get the energy that the fusion reaction makes out in the future to make things like electricity?
So in the fusion reaction, out comes a neutron. And so ITER will be a great big donut. It's a ring donut shape. It has 6 meters radius of that donut. And it will produce the fusions in the middle of that ring, and they will come out. The energy will come out as this neutron. Now, the neutron doesn't get captured by the magnetic field because it doesn't have any charge. And so it comes out and it comes into the wall. In an energy-producing reactor, we have something in the wall called a blanket. In the blanket, the neutron hits actually lithium in the blanket. It makes tritium, which is the fuel you put back in again, and it makes energy, which you extract as heat, and you drive a normal turbine out of that heat. In fact, in the world, there's so much lithium and deuterium that we'll be able to run fusion reactors for millions of years.
Assuming that we can get them working.
Yes.
Where actually in France is this happening, and what stage of the build are you now at?
It's being built near Aix-en-Provence. So nice part of France, actually.
Good wines there.
Yes, a nice rosé. Near Cadarache. And it's going to take about 10 years to build. So during that time, JET will continue to operate at Culham, and we're hoping to break all our records in the near future, actually get more fusion power out of JET than we got in the 90s.
Let's hope it works. Thanks, Steve. This is The Naked Scientist. We're talking about the science of fusion power, and also we'll be talking about what you should do when you put your grape in the microwave. Andrew in Cambridge has warned, don't leave your microwave on for more than 15, I thought he was going to say minutes, but it says 15 seconds. So don't zap your grape for more than 15 seconds. You should be able to see the effect with that long. Helen?
Right, well, we're talking the science of fusion, and this is a branch of science that's actually still quite young. So, as we're hearing, people are looking at different ways of achieving fusion in the lab. We're hearing about how different forms of hydrogen might be used at very, very high temperatures to create plasma, and from that, the fusion process might start happening. But now we have Kate Lancaster with us in the studio. She's from the Rutherford Appleton Laboratory, and she's looking at generating fusion using lasers. Now, hi, Kate. Thanks for coming on The Naked Scientist.
Hiya, no problem.
It's great to have you here. So first of all, why lasers? Where do they fit into this whole picture of fusion in the laboratory?
Okay, so ever since lasers were invented in the 60s, there was an idea that you could use lasers to drive fusion. Essentially, there's more than one way to skin a cat with lasers, but I'll describe the current most popular way of doing it. Essentially, it's like a petrol engine where you have a compression phase where you use long pulse lasers to compress a fuel capsule made of deuterium and tritium, the two isotopes of hydrogen that Steve was talking about earlier. And then the second phase is to heat this. Now, the long pulse lasers that I'm describing are a billionth of a second, so not particularly long in your field of view, but actually acres of time in laser terms. The point of compressing the capsule is basically in order to move the atoms much, much closer together. So you compress the material to basically hundreds of times solid density.
And how are you doing that compression?
So basically what happens is the laser hits the surface. So you've got symmetrically irradiated capsule, so you irradiate all round a sphere. The laser hits the surface and heats up some of the surface, which flies away. And basically, due to Newton's third law, the rest flies forward. So if you can do this symmetrically, all of the material flies forward and compresses together to high density.
So it's like a sphere, and it's all coming towards the kind of the core nucleus, if you like, of that sphere.
Exactly.
And you said that the lasers are very, very quick and short in duration. Are there lots of them? Is it a continuous stream of them coming on and off?
No. Essentially, this compression phase part takes the duration of the laser pulse. So a few nanoseconds, which is this billionth of a second, is a nanosecond.
But that's enough to heat up this sphere of matter.
The heating part comes next.
Okay, I'm stepping ahead. Sorry.
So basically, as I said, it's like a petrol engine. So you've done the compression part, but now you need the spark plug. And so what you do is you have an even more intense and more powerful laser beam, which is injected in. And what happens there is it actually, when it interacts with the dense material, produces hot particles, like electrons, for example, which then stream in and deposit their energy and raise it to the 100 million degrees centigrade that you need for fusion to occur. So this we know quite a lot about the compression side of things because, as I said, this has sort of been around since the 1960s. It's the spark plug bit, which is the sort of unknown thing, and what I spend most of my time trying to investigate, how these particles are generated, how they do the heating.
And so how is this, have you got this to work yet? Or are you still really fiddling around with that ignition part?
So essentially, laser facilities at the moment are only just being built which have any capability of really properly demonstrating such a technique. Now, there were proof of geometry. I'm not even going to say proof of principle experiments. There was a proof of geometry experiment, so that you could compress and inject some short pulse heating beam in Japan back in 2001. And they were very successful experiments, and they sort of spawned this whole field of interest, that really helped. But, essentially we have a lot of work to do in order to demonstrate it. But basically what happened, we're trying to get a laser facility built in Europe called Hyperlaser. It's not quite the same scale as ITER, but it's certainly going to be a very, very huge facility which will basically try to test this technique and try to get gain out of it, so actually get fusion energy out. I mean, it won't generate electricity, but again, it's going to be one of those things where we can actually try to prove the principle. So if you're interested in the details of the website, it's www.hyper-laser.org, and they'll find all the details of this project. We're currently in the preparatory phase at the moment. We've got money from Europe to really try and design this laser, so it's very exciting.
And I'm quite keen to know what sort of scale you think this might be on, and also, really, when is it going to happen, do you think? Well, if you had to take a guess on it, when are we going to see this?
Oh, as a sort of technique.
Or maybe when might it roll out as actually a way of doing this?
Okay, well, so the timescales are, I mean, Hyper is going to take sort of 8 years to sort of de-risk and design, and then should be operational by the early 2020s. So after that, it's going to be at least 20 years after that. So, it's a long-term thing. But the fact is, it's so attractive that you just have to continue to work on it.
So we're going to have you back in years to come to see what happens. Thanks.
I hope so.
Thanks very much, Kate, and good luck with all your research. And
thank you.
That's fantastic insight into how lasers might help us unpick the conundrum of fusion.
There's Kate Lancaster from the Rutherford Appleton Lab there. And this is The Naked Scientists with Chris and Helen. We're talking about nuclear fusion. If you have a question, the email address is chris@thenakedscientist.com.
Lifting the lab coat on the world's best science. The Naked Scientists.
This is The Naked Scientists, Chris and Helen, and now time to welcome to the studio Diana O'Carroll with this week's question of the week, of a fusion not variety, but it's certainly charged with interest. Diana, hi.
Well, hello. It's another supposedly clean form of energy. This week I'm getting all charged up to answer this question.
Hi, this is Alvin Raj from Cambridge, Massachusetts, and my question is it really better to let a battery completely run down before charging it?
So, do batteries really degrade if you leave them permanently full of chemical beans?
Hello, my name is Patrick Palmer from the University of Cambridge, Department of Engineering. This is a very good question that exercises me most mornings after I've cleaned my teeth, and I don't know whether to put my toothbrush back in its holder and charge it, or whether to just leave it on the side. There is some truth in the fact that a nickel-cadmium battery, which is the lightweight one, occasionally needs to be helped by being deep discharged. Most of the time, just discharging it 20% or maybe 10% and recharging it is okay, but it needs to be probably reset once every month or so, something like that. The lithium battery that's popular in telephones, of course, is also lightweight. These, however, do need considerable care, and that's why you find lithium batteries in mobile phones and in laptop computers. Their charging and recharging has to be monitored very carefully. They have protection circuits in them, usually. So, occasionally, it probably is a good idea to let your laptop run flat, but do that occasionally because that allows the computer to recalibrate itself and be up and running for the future. The other main type of battery, of course, is your lead-acid battery in the car. And in fact, we know very well that lead-acid batteries can work very well if they're just kept basically topped up the whole time. So care is required, and occasional deep discharge of nickel-cadmium, and for that matter nickel metal hydride, probably less often. Just by using it in the equipment till it's flat is probably not a bad idea.
So, NiCad, not naked, that is, batteries can degrade after a while if you don't fully discharge them every so often. And we had a great response on our forum from Wolfkeep and TechMind extolling the evils of NiCad batteries. Yeah, we don't like those anymore, and thankfully the European Union are going to chuck them out.
Why?
Well, because cadmium is poisonous. To most living things generally. So I think it's going to be nickel metal hydride from now on, and the lithium batteries you find in cameras, laptops and mobiles tend to self-regulate their charging, but even these can do with a full rundown too. Talking of needing power, what about this bicycle conundrum?
Hi, this is Bunny calling from Portland, Oregon in the States. On a recent trip from the farmer's market with a heavy load of fruit in my bike basket, I started to wonder if the placement of the load on the bike makes any difference in the efficiency of the work I do. Would it be easier for me to have baskets on the back where I would pull the load as opposed to on the front where I must push my load? Or is it simply too small of a system to make a difference?
So where's the best place to put the shopping? I've always found it's best to give it to a man to carry anyway. So let us know what you think by scribbling it down on the forum at thenakedscientist.com/forum or by emailing chris@thenakedscientist.com.
Thank you very much, Diana. The forum, of course, that Diana's mentioning there is our discussion forum on the Naked Scientists website, where there are people from all over the world putting their questions and then answering other people's questions. So it's a thriving hubbub of scientific interaction. So if you want to go and join in, nakedscientist.com/forum.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists, and so now it's time to go back to Ben and Dave, where they have been microwaving grapes.
Welcome back to Kitchen Science. We're still at Long Road Sixth Form College with Michael and Andy. And Dave, what have we got set up?
We have a grape which is cut almost in half, so you've got a little bit of skin holding the two halves together. Then opened up so the two halves are sitting next to each other in the middle of a plate, and we're just about to put it in a microwave.
OK, then, well, Michael, would you mind putting it in the microwave for us?
Sure, why not?
OK, it's going in a perfectly ordinary microwave, although it clearly has the scars of previous Kitchen Sciences in there. It's a little bit burnt on one side. Dave, is this your fault?
Might be.
So Michael's put the grape in there. Andy, would you mind shutting the microwave door and turning it on for us? OK, and while that's running, we need you to make sure you can both see the grape and let us know if anything interesting happens.
At the moment, they just seem to be spinning around in the microwave. Oh, they're fizzing and... spark, I think.
Oh, it's set on fire.
Yeah, huge spark.
So the grapes, as well as filling the microwave with steam, seem to spark and burn, almost like it would if you put something metal in the microwave.
Yeah, they're definitely sparking, and if we take them out and have a look at them...
Obviously, do be careful if you're trying this at home, because these could now be very hot.
What's happened to the joint between the two grapes, which was sparking?
It's sort of burnt together and stuck together now.
It looks burnt, Dave.
Yeah, that's pretty much what's happened. The way a microwave oven heats things up is it fills the chamber with lots and lots of microwaves. These are a form of light, a form of electromagnetic radiation. When these pass through an object, there's a very large electric field and a very large magnetic field. The larger electric field vibrating backwards and forwards, causing electric currents to go backwards and forwards in something which heats them up.
So it's these moving electric currents that means it's really bad to put something metal in a microwave.
Yeah, electric currents travel exceedingly well through bits of metal, and metal can reflect microwaves, so you can get problems if you do that.
But the grapes aren't made of metal, and we didn't put any metal in them.
Well, they conduct electricity fairly badly, but they still conduct it. If you've got two halves of a grape with a very, very thin piece of skin in between, you get quite a large current which is spread out over the whole grape, trying to get through that little tiny bit of skin. This means the skin's going to get incredibly hot, and all the juices are going to boil out, which means it gets dry, and dry grape doesn't conduct electricity. So you've got a big current trying to get through a gap. The current's going to try and jump that gap as a spark, and you see those sparks.
So actually, putting grapes in a microwave does make sparks. Did you expect that, Michael?
No, not at all.
It is quite a surprising thing to see. Have you ever put anything dangerous in a microwave?
Not that I want to say on radio, no.
Well, of course we have, and there's lots more of those at thenakedscientist.com/kitchen science. But Dave, what does this have to do with today's show? Today's show is all about fusion and plasma.
Well, the way that electricity can flow through the air in that spark is because basically the large electric field rips the electrons off the atoms. So you've got electrons and positively charged ions in the centre of atoms. These can flow in an electric field, transferring charge and therefore producing electric current. This gas with separate electrons and central ions is called a plasma, and all fusion is done using plasmas.
Well, who'd have thought you could make plasma in a microwave, and that's one of the things you need for fusion. So that's all for Kitchen Science this week, and we'll be back with more very soon.
So it's true, you can make plasma in a microwave using just a grape, but Dave did warn me that if you don't have a turntable on your microwave, you can get quite large balls of plasma, which might scorch the inside of your microwave, so please be careful. I don't want any damage to kitchen equipment going on. But we will have more Kitchen Science next week, and if you can't wait till then, you can find 50 fantastic experiments to try out at home in our very own Naked Scientist book, Crisp Packet Fireworks. Go and get it now.
And you can find out details about that on the Naked Scientist website, nakedscientist.com/kitchen science, where we've got all those experiments written up and you can see how to do them. We're talking about the science of nuclear fusion this week, as you may have guessed, and we have with us two fantastic people, that's Steve Cowley and Kate Lancaster. Got a couple of questions here for you, Steve. John in Peterborough says, nuclear power plants, how much energy actually remains in there once you've taken the rods out?
Well, of course, nuclear power plants aren't doing fusion, they're doing fission, right, which is splitting big nuclei up, uranium. And in a nuclear power plant, you only use a very small fraction of the uranium. So there's something like 50 times more energy left in there that we're unable to tap, except through what's called fast breeder reactors, which we don't currently do.
And how do they work?
Well, this is a long question. They work by using the fast neutrons from nuclear reactions from uranium to attach to the inert part of uranium, which is uranium-238, to make plutonium, and then plutonium can fission, like uranium-235. So that's a really complicated answer.
I've got a question here from Kenneth in Chicago, and he wants to know, why does the sun take so long to burn out? I think I'll throw that one to Steve as well. What do you reckon, Steve?
The sun's doing fusion very, very slowly. It doesn't have to do it any faster to keep itself held up. If the sun did fusion faster, it would expand, and then the fusion would go slower and it would contract back down again. If the sun was doing fusion too slowly, it would contract until the fusion got fast enough to hold it up. And so the sun is just self-regulating, and that's why it's going to last about 5 billion years.
It's a sort of self-regulating system. That's great.
Got a question here from Ken as well. He said as part of the same email, said, can nuclear fuel from power plants be recycled indefinitely so there's no waste? And I guess how would that apply to fusion? Because you were mentioning that fusion generates its own fuel anyway, in a sense, because you can put lithium around the outside.
So with the current designs we have for fusion power stations, of course, these are conceptual. We haven't built one yet. But the current designs, we burn deuterium, which you extract from seawater, and we burn lithium, which you can get from salts. And as I said, there's millions of years' worth of this fuel. But the byproduct is helium, which, you can put in kids' balloons if you really like. And they don't have any long-lived wastes from this. So it's really kind of an ideal way to make energy.
And Kate, Martin says that the techniques you're talking about in terms of using lasers to ignite and sustain fusion, is that what's going to happen in ITER?
No, ITER is, as Steve pointed out, is a completely different device in terms of it's a big magnetic donut, essentially, and it confines plasma for a length of time. Whereas the thing about lasers is what you have to do, the reactor would be slightly different. You have to inject these fuel pellets and compress them, and in order to support a 1 gigawatt reactor, you'd need to do that 4 times a second. So the designs of the two systems are very different. However, that's not to say we don't have overlap and sort of they're not complementary, because they are. We have some of the same technology challenges.
Thank you very much. Well, unfortunately, we've run out of time, but I have to say a very big thank you to our guest this week. That was John Bailey talking about Japanese knotweed, and then our 2 fusion experts, Steve Cowley and Kate Lancaster. Also to our production team, Mira Sinthalingam, Diana O'Carroll, Ben Valsler, Dave Ansell and Tom Simpkins. Next week, we're going to be finding out about the human psyche. Basically, why do we perceive people as attractive? How can we make ourselves look more attractive? And why does a drink, an alcoholic one, stop you interpreting other people's emotions properly? We'll also be finding out a bit about the science of post-traumatic stress disorder. If you'd like to send us any questions, it's chris@thenakedscientist.com.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.